If you don't cap the queue, YouTube traffic will build back pressure that keeps P95 under control. By the end of this video, you will understand a small practical pattern to protect LLM endpoints from overload and produce predictable tail latency. I'm Professor Pi, teaching AI engineering and LLM systems with simple Python. Back pressure matters when your model endpoint faces bursts. Without limits, requests pile up. Latency balloons for everyone. Success looks like steady P95 numbers and graceful responses instead of timeouts. We will build a tiny test harness that simulates an LLM endpoint. Then add two simple protections: a concurrency gate that sheds excess work, and a short deadline that triggers a degraded fallback. That combination is the essence of back pressure for endpoints. First, we spin up a tiny FastAPI test harness to prove the loop works. This snippet creates a minimal FastAPI app and confirms the TestClient can reach it. The variable app holds the server, and TestClient wraps it so we can make HTTP calls without starting a real network server. The call client.get asking for the route path hits an undefined route, so FastAPI correctly returns 404. Keeping a persistent client is handy for later steps where we add endpoints and measure behavior under pressure. With this in place, we'll progressively layer back pressure policies onto actual routes. The printed 404 confirms FastAPI is running and the client works as our testing harness. Next, we model what a slow LLM call feels like by adding a single slow endpoint. This example introduces a slow/gen endpoint in FastAPI to mimic an LLM call. The function gen sleeps for 30 milliseconds using the time module to simulate compute or network latency. It returns a tiny JSON payload to keep the focus on response time rather than payload size. We then call the route through TestClient with the client.get/gen and capture the response. Increasing the sleep increases latency and tail risk, while decreasing it tightens P95 and overall responsiveness. The printed 200 shows the endpoint is reachable and provides our baseline before adding back pressure. Then, we intentionally add a crude concurrency gate to shed work at the edge. This code adds a concurrency gate to FastAPI using BoundedSemaphore. The variable SEM starts at 0, meaning no worker capacity is available. In the function genGate, we try to acquire the semaphore without blocking. If acquisition fails, the request is shed immediately. Returning OK indicates whether capacity was available. A real app would release the semaphore after work completes. But here, we hold it at 0 to show predictable shedding. Increasing the semaphore's initial value raises allowed concurrency, and decreasing it tightens the gate. The printed false confirms the gate is active and shedding work under 0 available slots. After that, we add a per request deadline so slow requests fall back quickly. This snippet adds a per request deadline in FastAPI to enable degraded mode. The variable T0 captures a start time with perf counter. Then, the function simulates LLM work with sleep. Afterward, degraded becomes true if elapsed time exceeds a 10 milliseconds budget. In practice, a degraded response would be a short safe fallback, such as a stubbed summary or cached hint, instead of waiting for full generation. Raising the budget reduces degraded responses, but risks higher tail latency. Lowering it aggressively protects P95. The printed true shows the budget was exceeded, and a degraded path would trigger. Finally, we combine both protections so they cooperate under load. This example composes two protections in FastAPI, a concurrency gate and degraded fallback. The variable sem2 holds capacity. Acquiring it means we can run the full path. Otherwise, we immediately pick a fallback. The function genCombo sets mode to fast if capacity is available, or fallback when overcapacity. In a real LLM app, fast would call the model, and fallback would return a cached or templated answer. Increasing sem2's capacity flips more calls to fast, while reducing it prioritizes stability under spikes. The printed fallback confirms load was shed and a safe degraded response was chosen. In a real project, you map these pieces onto your model pool and cache layer. The gate maps to worker slots or API concurrency limits. The deadline maps to a short budget, after which you return a cached summary or concise hint. Together, they keep P95 stable while allowing occasional full generations. Recap: what it is: a lightweight backpressure pattern that sheds and degrades to protect latency. When to use it: when tail latency matters more than perfect outputs during spikes. One caveat: aggressive shedding or tiny budgets can reduce quality, so tune conservatively. Next step: pick one knob and tune it under load. For example, raise or lower the semaphore capacity to observe how error rate and P95 trade off. If short, practical AI engineering helps, subscribe and watch the AI engineering videos.